Welcome back to the data mining class. So today we'll talk about Bayesian classification, which is a family of machine learning algorithms. So as you remember, classification is about taking a series of objects of different types, different shapes, and having an algorithm that is capable of saying this object belongs to that class. So this is about, this is what classification is about. So we have seen that many machine learning algorithms that are the backbone of classifiers follow a diagram which is based on the following ideas. We have a function that is supposed to achieve the task. This function is unknown, it's ideal, and this function is simulated by the data set we have. So the data will play the role of the ideal learning function that we don't know. We have a learning function that is not optimal. And we have a learning process whose goal is to optimize the parameters of the learning function so that the output of our learning function becomes very similar to the output of the ideal learning function. And very similar is calculated by using, an error function. How many times did my function give the same result as my ideal function versus how many times it gave the wrong classification. Now, in between, there's some tuning that happens to optimize my learning function. And we have seen an example of that with the linear regression with a gradient descent algorithm, where the goal was to find the equation of a line that ideally separates that ideally simulates the distribution of the points so that we can actually predict, given an x, the value y of that algorithm, and the gradient descent with its progress, which is supposed to stop or to converge at a point where the error or the distance between the ideal function and the actual learning function, our function, is minimum. Okay. Now, today we'll see a new type of classification algorithm that is not that does not follow this, schema, which is but it's still an interesting and very commonly used. So let's start first, since it's a probabilistic approach. Let's start first by doing, a very quick reminder of some basic probability rules. So as you see, we have first here the product rule, which is about the probability of occurrence of co-occurrence of two events. So we have event A and event B. So what is the probability of seeing both of them occurring together? So we can think about event A as, for example, sunny, and event B being dry. So in this case, obviously A and B are not mutually exclusive. If they were mutually exclusive, there's no reason to do any probability calculation or anything. The probability of their occurrence together is zero. For example, the probability that the door is at the same time closed and open is zero because these are mutually exclusive events. But dry and sunny, these are not mutually exclusive events. Okay, so now what is the probability of these two events? It is equal to the probability of the first given the second times the probability of the second. So what is the probability of seeing dry given that it's sunny times the probability of seeing sunny? Now, what is the probability of dry given sunny? This is something that we should calculate. It's really simple. We just need to count how many days, in how many days we have seen dry and sunny, and how many days we have seen dry versus how many days we have seen other, types of weather. So this is how we calculate probability of A and B, but also we have another way to do the same thing. We get the same result by saying what the probability of B given A. So what is the probability of dry given that it's sunny times the probability of sunny, for example. So this is the product rule. The sum rule is actually here we have the OR operator. So obviously here, so what is the probability of seeing an event A and or event B? So it's if either A or B are observed, then actually that's fine with us. So in this case, it's logically the probability of event A plus the probability of event B minus the probability of seeing them together. So here, I either should see A or B. Now, if we go back to the same example, so sunny or dry, so what is the probability of seeing sunny or dry? Okay, so these events, they can occur together, but they can occur not together. So we can have dry and cloudy, for example. So now this is not very likely, but that's not impossible. The idea is the two events are not again mutually exclusive. If the two events are mutually exclusive, then actually this term would be zero, and the probability of both events, if they are mutually exclusive, would be probability of A plus probability of B. So either this one or that one, and I think that makes some sense. We also have the third, thing that we need to know is actually the probability of total, that's theorem of total probability. So given that we have n mutually exclusive events, AI, AN, so again, examples of mutually exclusive events. Suppose we have a weather forecast, so it's either sunny, cloudy, or rainy. So it cannot be at the same time sunny and rainy. So these are mutually exclusive. And if it's cloudy and rainy, then it's actually rainy. But if it's cloudy, then it's not rainy. So that's sort of, yeah, so that makes sense. And these three events are mutually exclusive. And so suppose these are the only three possibilities we have. In this case, the sum of the three, the sum of the probabilities of the three events is equal to 1. Okay, in a place where we only can see the three, forecasts, the sum of their probabilities would be equal to 1. Okay, so now let's talk about the theorem of total probability. So suppose we have n mutually exclusive events, AI, A to n. So this could be 1, 2, 3, 4, 5 events. The probability of these events sums to 1. For example, the forecast of the weather in a given area is either cloudy, rainy, or sunny. So the sum of the probabilities of these three mutually exclusive events is 1. Obviously, the weather cannot be rainy and sunny at the same time. So these are mutually exclusive events. So how we can calculate the probability of a given event, of an event given these three possibilities, we do that with the following, formula. So the probability of this event is equal to the probability of this event given A1 times the probability of A1, the plus the probability of this event given the event A2 times the probability of the event A2, so on, so forth. Okay, so let's take the following example. Suppose that we have an area, we live in an area where there are two factories that make cars, only two factories that can supply cars in this area. So factory X and factory Y. So suppose that factory X's car have a 99% chance to go beyond 200k miles. And suppose that factory Y's cars have a 95% chance to go beyond 200k miles. And suppose that factory X supplies 60% of the cars in this market, while factory Y supplies 40% of the cars in this market. So it's easy to see here that A1, which is the event that a car is actually going beyond 200 miles, X's car going beyond 200 miles, and A2, Y's car is going beyond 200k miles in 95%. See, these are two mutually exclusive events. So if a car is made by X, it's not made by Y, and vice versa. So that's an important thing to notice. So now, based on this information, we can ask the following question. We have a lambda car, a car unknown. So, and we would like to know in this area, we live in this area, we have this unknown car. We don't know the make of this car, but we would like to know what is the chance that this car in this area, what is the chance it's gonna go beyond 200k miles. So to calculate that, we need to go back to this previous equation, which is about the sum of the probability of B given A1 times A1. So what is the probability of a car going beyond 200k given that it's made by X times the probability that the car is made by X plus the probability that the car goes beyond 200k given that it's made by Y times the probability of the car being made by Y, and we can obviously see that. So here, in 99% of the cases, the cars made by X go beyond 200k, times 60% of the cars are made by X, plus 95% of the cases, the cars made by Y go beyond 200k, times 40% of the cars in the market are made by Y. So basically, we get this result. So Bayes' theorem is another statistical tool that can help us based on observed values, based on observed facts, we can predict future events. And in our case here, we would like to do some classification, but we'll see that in a later, moment. At this time, so it's interesting to see that we have a hypothesis H, and we have some data or observed facts D. What is the probability of a given hypothesis, of a hypothesis given that we already observed D? So basically, we need to understand that with a concrete example. So suppose we observe that the weather is humid. We would like to calculate the probability of seeing rain, given that we already observed that it's actually humid. Okay, so how we do that? So according to the Bayes theorem, we need to find the probability that it is humid when it's raining. So if it's already raining, how likely it is to be humid, the weather. Now, second, we need to calculate the probability of the hypothesis itself, which is probability of the rain. So obviously, if we live in a dry area like, New Mexico, Arizona, things like that, the probability of rain would be low. And if we live in a rainy area like, Washington State, the probability of rain would be higher in this case. Now, one can ask the following question, which is legitimate. So how can we find this probability of of the weather being humid given that it's rainy? So basically, what we need to do is actually to collect some data. Suppose we have a sample of 100 days of weather data of 100 days, 1,000 days, 1 million days, whatever sample. Obviously, the bigger the better. So we count how many times it's humid. The humidity is high when it's raining versus when the humidity is low when it's raining. So we find it's just a counting mechanism, and this is how we get the probability of the weather being humid, which is our observed facts here, given that it's raining. And also, we have to calculate how many times in the area where we live, how many times the weather is humid and how many times the weather is dry. Okay, so basically, this is what Bayesian theorem is good for. It's good for predicting some future facts based on observed facts. Okay, so H is the hypothesis and D is the observed facts or the data. Let's take a first example. So we have a patient that takes a lab test and the result comes back positive. So suppose we are testing for cancer. So suppose that we know that our test returns a correct positive result in 99% of the cases. So in 99% of the cases, when we tell the patient you have cancer, 99% of the cases, the patient does have a cancer. But in 1% of the cases, the patient does not have a cancer, which is not a good thing, obviously. Now, the second thing is actually when the test is negative, the result is 95% accurate, which means that if we say you don't have cancer, in 95% the patient doesn't have cancer, but in 5% of the cases we say you don't have cancer, but actually the patient does have cancer. So now, if we also assume that 0.03% of the population has the cancer, so we have only 3% of the population that has cancer, so we can ask the following questions. What is the probability that this patient has a cancer? If his test is positive, if his test is negative, etc. What is the probability that he does not have a cancer? What is the diagnosis? So given all these questions, we can plug the numbers. If the result is positive, if the result is negative, we can plug the numbers and give a good answer based on the Bayes theorem. Okay, so now what we have seen so far is actually we have a hypothesis that we wanted to test. So what is the probability that it's going to rain, given that we already observed that it's humid? So that's the example we have seen. But this is not a realistic situation, because in the real world we have multiple hypotheses that we would like to test, and we would like to select the one that is more likely, that has the highest probability. So if we go here, what we are after actually, so is the hypothesis that maximizes this probability. Okay, so here big H is a set of hypotheses and small h is one of these hypotheses that we are testing. So let's go back to our example. We have observed that the weather today, that we have a high humidity. Okay, so this is the data we have, and we have three hypotheses to test in this case. First hypothesis, it's rainy. Second hypothesis, it's cloudy. Third hypothesis, it's sunny. Okay, so hypothesis 1, hypothesis 2, and hypothesis 3 will be tested, and we will select the one that maximizes our probability. So argmax is just basically we are selecting the hypotheses whose probability is the largest. Okay, so that's what we mean by argmax. So basically, we just replace this with what it means in Bayes' theorem. So probability of D given H times probability of H over probability of D. Now the point is, since we are testing the three hypotheses, given the probability of the data, so the probability of the data will be the same with hypothesis 1, hypothesis 2, and hypothesis 3. So since it's we are dividing the three hypotheses by the same value, so that the probability of D will cancel out in the three cases. Now, in case we have a situation where the three or the n hypotheses that we are testing have exactly the same probability, so we talk about, in this case, uniform prior. So multiplying by probability of H would be meaningless. So suppose we live in an area where in 33.33% of the cases it's rainy, 33.33% of the cases it's cloudy, 33.33% of the cases it's sunny. So yeah, multiplying by the probability of H would be meaningless. So in this specific case, not in all the cases, but in this specific case, when we have uniform prior or uniform distribution of the probabilities, in this case, we just need to calculate probability of D given H, and that would be enough. What makes Bayes classifier an attractive framework? First, it's incrementality. So we have a training example. With this training example, we can calculate the prior and the likelihood. They can be updated dynamically. So we can also combine prior knowledge and observed data. And interestingly, and that's actually what makes it more attractive than many other competitors in machine learning, we don't only say, and I think this is the most important feature here, we don't only say that an item belongs to class 1 or to class 2 versus class 3. We say it belongs with class 1 with this probability, it belongs with class 2 with this probability, it belongs with class 3 with this probability. So we have a confidence score associated with our classification, which is not the case with the other machine learning paradigms. Now, we have seen the basic framework with Bayesian learning. So how can we apply that to machine learning? So we have seen actually examples of how we can predict future event based on one data. Now, the question now is how can we use the Bayesian theorem for machine learning and for classification? The idea is really simple. In the previous examples, we have seen the probability of the hypothesis given one observed data. Here, we can simply say what is the probability of the class given x1, x2, xn, knowing that x1, x2, xn are actually features in our data set. So what we would like to see is, obviously here we have multiple candidate classes for our classification task, the simplest one being binary classification, where we have two classes. In more complex situations, we might have larger number of classes. Usually we don't go beyond 5, but there are some research about larger numbers of classes. Now, when with the number of classes is infinite, this is not classification anymore. This is called regression, and we have seen the example of linear regression. So what we actually, if we replace this with the Bayesian theorem, so we would like to see the probability of x1, x2 up to xn given the class times the probability of the class divided by the probability of this sequence of features. And the simplification, given that we are testing different hypotheses, we would simplify to just multiplication of this sequence of features given the class times the probability of the class. Now, the problem here, there's a problem here, which is simple, but at the same time, it's a little bit subtle. The point is, here, we are calculating the probability of observing a given class given a set of features. So this number of features can be 2, 3, 4, or even actually much bigger. So I've done some classification with more than 100 features. The problem with that is actually having the exact same combination is really hard to observe, because the bigger the number of features, the bigger the combinatorics of these features, and it would be hard for us to have enough data where we can see this exact same combination CJ with value x1, x2 up to xn. So this would require us a huge amount of data to have enough representation of this whole sequence with CJ, and enough representation with this whole sequence with another class, and so on and so forth. So this would require a tremendous amount of data that is usually not available, and especially again when the number of features is really big, this is simply impossible to have. So the solution is actually, interestingly, we can have a mathematical simplification And this mathematical simplification, although actually with any simplification we would lose some information, but in this case, practically, the classification would work fine. So that the cost of this simplification is really very small, practically. So this solution is called the independence assumption. The idea is really simple. So we would assume that the probability of the feature and the class will not depend on the occurrences of the rest of the features. So we would say probability of C of the class of the feature x1 given that class Cj uh, is independent from the probability of the feature x2 given the class Cj. So with that assumption, we can say that the probability of this whole term is equal to the multiplication of the individual probabilities. So xi given cj, we will multiply, for example, x1 given cj times x2 given cj times x3 given cj up to xn given cj. So this is an interesting simplification, and it's very good for reducing the amount of needed data. Now, a small thing that needs to be added here. Let's take an example. Suppose that we live in an apartment, in a building, and that we are observing the weather. So we have outlook, temperature, humidity, and wind. So we have 4 features in our data set. So these are things that we are observing. And also in our data set, we can look from our window at a tennis court, and when the weather is, when the outlook is sunny, when the temperature is hot, when the humidity is high, when the wind is weak, so people don't play tennis. Suppose in second day, we could see that when the outlook was sunny, the temperature was hot, humidity was high, wind was strong, people also don't play tennis, so on and so forth. So we could collect this data set by observing the weather parameters as well as yes or no people were playing tennis. So this is our data set. It's made of 14 data collected in 14 days. Now, we need to train our Bayesian classifier with this. So we have for the outlook, the first parameter in our data set. So the outlook, let's look here. We have 9 cases where people play tennis versus 5 cases where they don't play tennis. And we just need to count that. So 1, 2, 3, 4, 5. So 5 no and 9 yeses. So this is where we got 9 and 5 here. So that's very important. Given this data set, how we can do the Bayesian learning. So Bayesian learning would work the following. So first here, we take the first feature, which is outlook. Outlook has 3 possible values, sunny, overcast, and rain. And so we have 9 cases where it's actually where people do play tennis, and 5 cases where people don't play tennis. So over the cases where it's sunny, 2 were positive, people were playing tennis, and 3 were negative, people don't play tennis. So this feature is not helping us a lot in saying yes or no, people play tennis or not. When it's overcast, people never, yes, people always play tennis and they never don't play tennis. So that's a good indicator. Rain, when it's raining, so in 3 out of 9 cases they play, in 2 out of 5 cases they don't play. Now humidity, when the humidity is high, 4 out of 5 they don't play, so on and so forth. So we actually make some observations like that with every one of these features and with every one of the values of every one of these features. After this learning phase, we need to apply that to a new set of features. So suppose that we have a new x, a vector of features. Outlook is sunny, temperature is cool, humidity is high, wind is strong. So you can imagine actually here that we can encode this with a vector saying 0, 1, 0, 3. So every one of these, features would have a coded number, but just for simplification here, we're just representing that with their actual values, but in a real data set, we wouldn't use that. We can encode the variables with numeric values. And that's why we get a vector, like a NumPy vector, for example. So now looking at the tables that we have in the previous slide, we can say that the probability of the outlook being sunny, given that people play, given that people play and the value in this case would be yes, so it's 2/9. The probability the temperature is equal to cool, so here we actually temperature is equal to cool, probability equal to cool, and the probability given that people are playing, so it's 3/9. Probability of temperature is equal to cool given people don't play is equal to 1/5. Probability of humidity is high and people play is equal to 3/9. Probability of humidity is equal to high and people don't play, given that people don't play, is 4/5, so on and so forth. And based on these, we calculate the probability of all these features given the first class and given the second class. Here we have a binary classification, class 1 and class 2, and we plug these numbers into our Bayesian equation, and we take the one that maximizes our our probability. So here the probability of yes given our observed facts is 0.0053, while the probability of no given our observed facts is 0.002, so 0.02, which means that actually no wins, and because it has a higher probability. Okay, so far we have seen the Bayesian formula and how we can use it for classification. Now the question that we can ask ourselves is the following. Is Bayesian classifier a good choice in when to use it when we have a classification task? So this diagram is a very interesting one. It shows the really big advantage of Bayesian classification, which is that it's a very good classifier to use when we have a small data set. There are so many machine learning algorithms that are better in general, that do a better job than Bayesian classifiers. However, these alternatives require bigger data sets. As we can see here, even with a small size of training set, the performance isn't bad. And as we can see here as well, the performance increases drastically even with small increases of data, which is great. We have seen that the probability of the class given the set of features is hard to calculate in one piece. That is why we broke down this probability into probability of the class given feature 1, probability times the probability of the class given feature 2, times the probability of the class given feature n. Now, this assumption is called naive because in the real world, we have something called time series. So things are not that simple. So the variables are interdependent of each other. And for example, assume you are trying to recognize the digits of a zip code, for example. So these digits follow a given pattern. We cannot assume that the digits are independent of each other, and that is why the naive assumption does hold in some cases, but it doesn't hold in other cases. So let's try to take an example, a formal example, to demonstrate a case where the naive assumption or the independence assumption fails. And this example is the XOR or exclusive or logical OR assumption. So in a normal OR, so when we have variable x1 and variable x2, OR would be false only in one situation where both x1 and x2 are false. To prove that OR is true with a normal OR, we just need to look at one variable, in other words. So if the variable is true, we don't need to look at the other variable. Right away we decide the OR statement is is true. However, with the XOR, we need to keep our eye on both variables. So because the XOR statement is only true when one of the variables is true but not the other. So if we look at this table here, the XOR statement is false here because both are false. It is true here because one is true, one is false, one is false. It is true here because one is true, the other is false. So the naive assumption or independence assumption doesn't work because I need to keep my eye not only on one variable, but on the value of both variables. So if you're not comfortable with logic, let's take a real world example. And then a real world example of the XOR statement is actually, suppose we have a restaurant that gives a gift to its guests at the end of their meal, and this gift is coffee or ice cream. So if the restaurant gives coffee, the customers will be happy. If the restaurant will give ice cream, the customers will be happy. But if the restaurant gives coffee and ice cream, people won't be happy because they would see that as being strange. And you imagine somebody eating ice cream and drinking coffee at the same time. So that would be funny. Okay, so in many cases, almost never, the naive assumption is not true because the variables are interdependent. But practically, and again, practically, this is an empirical question, so you need to measure that practically, it helps solve the problem. Since we are dealing with probabilities, there is a well-known issue with probabilities actually, which is the multiplication. With the naive assumption, we had to multiply the probability of the class given, again, feature 1 times the probability of the class given feature 2 up to feature n. And if we have a huge number of features, so we will end up with a really small number. And here I gave you an example. If we have to multiply 2000, the probability of 2000 independent coin flips, we will end up with something that is 0.5 to the power 2000. And for MATLAB, for example, which is a well-known tool for mathematical calculation, for MATLAB, this number is equal to 0, which means that we lost the information. After some repetition, we will end up with a number that is so small that MATLAB considers it as equal to 0. So now how to solve that problem? So this problem is in math called floating point underflow. To solve it, we will actually take the logarithm of the multiplication of the probabilities. So we know for a fact that the logarithm of x times y is equal to logarithm of x plus logarithm of y. So this is a kind of trick to help us turn the multiplication into addition, and by doing this, so we will solve the underflow problem. Now, would that change anything in our situation? Actually, no, because we are keeping the scale. So we have some hypotheses. So in this case, our hypotheses are our classes. CJ, a member of the set of the classes. It's, again, in the simplest possible scenario would be we would have two classes up to a given number of classes. So in this case, we just take the logarithm of the probability of that class times the sum of the probability of every feature given the class. Instead of the multiplication, now we are doing a summation, and that solves our problem. What are the advantages of using naive classifiers? So first, it's simple, conceptually simple. It's based on probability theory, nothing really fancy. Second, it requires small training data set. It is fast computationally, and it scales linearly with the number of features and training examples. So there, the computational complexity isn't bad, and it can handle binary classification, like is this animal a cat or not a cat, versus multiple classification, is this animal cat, dog, mouse, lion, etc., whatever you want. Now, what are the disadvantages of the naive Bayesian classifier? So first, I mean, it's naive, so the independence assumption is is okay in many cases, but again, it doesn't hold true, and we have seen a very good counterexample with the XOR. So it doesn't work in all the cases. It works in many cases, but not in all the cases. And that is why in many cases it actually gives poor estimation of the probability based on that. Out of this presentation, so naive Bayes is really easy to implement and often works well. It's often a very first it's often a good algorithm to try for first experiments, and it's commonly used as a kind of ingredient for more complex or smarter machine learning algorithm.